Alright, so here's a couple of warm-up problems for you to try before we get into the lesson. So pause the video and try these. Hopefully you tried these problems first before I go through them, but we have some review of solving equations. So number one, you have 5x minus 7 is equal to negative 12. To find x, remember what we try to do is we try to isolate the variable. So we try to get rid of the 5 and get rid of the 7 here. Basically move it over here to get x by itself. But make sure that you use correct steps for solving equations. So number one, if I want to get rid of minus 7, I need to add 7. Now I'm going to write it like you guys typically do. I'm going to write the plus 7 underneath, even though technically, remember I told you that does leave some of you making mistakes a lot of times because you accidentally divide when you should be adding. But I'm going to write it like you guys. Negative 12 plus 7 is negative 5. Use your calculator if you can't do that in your head. Then we divide by 5 to get rid of multiplication. Notice in both of those steps that I just showed you, what I do to one side, I got to do to the other. What I do to one side, I got to do to the other. So whatever I put in the problem that wasn't there before, I have to make sure I do the exact same thing on both sides. So when you divide 5 here, 5 divided by 5 is going to be 1x, so it gets x by itself. And negative 5 divided by positive 5 is negative 1. So there's my solution for the equation. Remember what we mean by the solution. We mean that negative 1 is the answer, that if you plug in negative 1 right here for x, it will give you negative 12. So let's take a look at the next one. 6 equals 3 minus x. Be careful on this one because it's not minus 3. That's actually a positive 3. So you need to subtract 3 from both sides. When you subtract 3, you're still going to have a negative x. 6 minus 3 is 3. Your x right here is still not by itself. So you still have to actually divide by negative 1 to get that to be a positive x. 3 divided by negative 1 is negative 3. Number 3, you have x divided by 4 is equal to 12. What's the opposite of division? It's multiplication. So we're going to multiply by 4 on this side. We're going to multiply by 4 on this side. So if you multiply by 4, it cancels that 4 out and leaves me with just x. 4 times 12 is 48. Again, think about it. Again, that's the answer, 48, right? If you plug 48 up here, 48 divided by 4 is 12. The last one, number 4 here, 8x equals 32. It's 8 times x, so that's when you use division. We divide by 8 on both sides, and we get x is equal to 4. Now, number 5 actually kind of leads into what we're talking about a little bit today. With equations, you get one answer, that solution there, that gives you and specifically linear equations is what these are, because x to the first power. You get one solution that works for x, and you can tell by plugging it back in if it's going to be the solution or not. With inequalities, you have to be a little careful because it's not just equal to that you're looking at. With an inequality, you have that less than symbol or greater than symbol. But sometimes you also have less than or equal to or greater than or equal to. So you have to be careful. It leaves the opportunity for more possible solutions. So number 5 asks you just to check and see if x equals 4 is a solution to 3x is less than 12. So what that means is we're going to plug in 4 and see if it works. So if I plug in 4 for x, 3 times 4 is 12. Is 12 less than 12? Now, normally, if we solve this right here, we'd say, oh yeah, it's the answer. But again, this is not an equation. This is an inequality. So it says less than. So it's telling you that this 12 right here is bigger than this 12 because the alligator's eating this 12, right? But that's not the case. 12 and 12 are equal. So that means 4 is actually not a solution for this inequality. So how do you find solutions for inequalities? That's what we're going to be looking at in this last chapter. This is our last chapter of the year. We're going to be looking at what are solutions to inequalities. So, first of all, we're going to talk about graphing inequalities. So today, this is the last chapter of the year. You don't really have to label it this if you don't want to. We're going to be solving one-step linear inequalities today. But before we solve inequalities and we learn how to solve them, we're going to talk about the graphs. The graph of a linear inequality in one variable is the set of points on a number line that represent all the solutions of the inequality. Now again, we're just talking about one variable inequalities right now. We will get to 2 variables before the end of the year. So what I'm talking about is, how do I represent something like x is less than or equal to 3? Well, if we represent it just in words, we're saying that all of the x's are smaller than or equal to 3. That's what less than or equal to means. So we're saying all the values for x have to be numbers that are smaller than 3 or equal to 3. So think about a number line. If you have a number line, and I'm going to put just 0 here, it doesn't have to be perfectly in the middle. And I've got 1, 2, and 3, and 4, and 5 going this way. I've got -1, -2, -3, -4 going this way. What numbers are less than 3 or equal to 3? Well, if you think about it, it's everything. All these numbers right here are less than 3 until you get to 3. And 3 is the only one that is equal to 3. So what we do, and I've got a little note underneath here, is if we have a less than or greater than symbol, we use an open dot. If we have a less than or equal to, greater than or equal to symbol, we use a solid dot, or bubbled in dot if you want to call it that, to represent x could be 3. And then we shade all the other numbers that it could be as well. And so you'll see me when I'm drawing my shading, I kind of do this little squiggle on the graph this way, all the way down towards that end, because every single one of these numbers this way are less than 3, or with a solid dot, equal to 3. Now, some teachers also teach to do a solid dot like this and then draw an arrow above the number line pointing this way. That's okay with me. That doesn't bother me if that's the way you want to think about the labels. But for me, I like to shade the actual line. That's just my personal opinion. That's the way I learned it when I was in high school myself. So that's how we represent in a picture visually the solutions for an inequality. Those are the numbers that are less than or equal to 3. We can do the same thing when the numbers are something like x is greater than -2. So I'm going to draw myself a little number line again. Now this one I'm not going to draw as gigantic of a number line as the one up here. And guys, that's the thing. You don't necessarily have to draw a huge number line. I'm going to put 0 here, -1 here, -2, -3. I'm going to put an extra number up here, 1. Also notice I don't put every single number in the world on there, and I kind of focus in on the one that I'm looking at. It is -2, and numbers for x are greater than -2. So the alligator's eating the x. Again, that means the x is bigger. And guys, I know that's sort of a kindergarten way to think about it when you think about the alligator eating the bigger number. But honestly, guys, that's still what goes through my head when I look at an inequality. I know that sounds really stupid, but when I look at x is greater than -2, I'm saying the numbers that are bigger than -2. So I'm talking about these numbers over here. -1 is bigger than -2. 0 is bigger than -2. 1 is bigger than -2. But so is right here. -1.9 would be bigger than -2. So the way that we represent that to let someone know is that we say we put a little open dot right here because it can't be equal to -2, but all the numbers bigger than -2 will work, and so we shade this way, bigger than -2. And a little open dot lets me know that it's not equal to. Okay? So the equal to tells me to do a solid dot. The not equal to tells me to do an open dot. And that is just a visual way to tell somebody and to tell myself what numbers actually work for x. So what I have is a couple of problems for you to try graphing on your own. So I want you to try graphing these, and then I will put the solutions up on the video. So pause the video and try them before you watch the solution. So again, hopefully you paused the video and tried them first. Well, obviously I can't be watching you making sure you did that. But x is great or less than, 2. If I put a couple numbers on here, I'm going to say I put 0 here, 1 here, 2, 3 here, -1's here. And I draw a open dot because it cannot be equal to 2, and shade everything that is less than 2. Notice the x is less than 2 because the alligator's eating the 2. And that means the bigger ones. Then we have x is greater than 2. So essentially the same type of numbers that we're looking at here. But this time we're looking at numbers that are bigger than 2. So we're talking about an open dot this way, shaded to the right, because those are the numbers that are bigger than 2. Now the reason I put these two on here that have the same number is because I want to point out something. There are some people who oversimplify things and say, oh, I get it. All you gotta do is shade which way this thing points. Shade which way this thing points. That's all you gotta do. And then they forget that they're actually talking about numbers that are bigger than 2. That's why we shaded, not because of where something points. X is less than 2. That's why we shaded to the left on this one, because it is numbers that are less than 2. Not because that's the way the arrow points. And so I want you to be careful with that. And let me show you real quick what I mean by that. If I gave you, let me draw it in orange since I'm using this one here. If I gave you this right here, a lot of you would say, oh, look at where it points. Shade that way. It'll look like this one. But you would be wrong. This right here, what is x? X is not bigger than 2. X is actually still less than 2 because look at this. The alligator's eating the x. 2 is greater than x. That means this shading is actually still this. So that's where you have to be careful. You can't just assume just because something's pointing some way. You need to know what is x. Is x greater or is x smaller? That's what you need to know. All right, so in the last two here, we got x is less than or equal to 1. If you looked at this guy, you would have a bubbled in or solid dot at 1, and less than would be numbers that are this way, that are smaller than 1. And then the final one, x is greater than or equal to 0. You would have 0, and you would have a solid dot at 0, and greater than 0 would be this way. Again, notice the open dots when you don't have equal to, and the solid dots when you have equal to. Again, pay attention to your shading and realize what is x. Not which way anything's pointing, but what is x. Is x smaller or is x bigger than a number? That's what you're looking at, and so you're giving a visual representation of what the solutions are. Now, how do you actually find these solutions when you have an inequality? Here's an example of a little word problem. It's a little short word problem. You may want to try it first, see if you can figure it out. Struggle through it a second before you watch the solution. So you can pause it here. So Sue ran a 2-kilometer race in 8 minutes. Write an inequality to describe the average speeds of runners who were faster than Sue. Graph the inequality. Well, first of all, we need to know how fast was Sue. Because if we're looking to try to write an inequality for people that were faster than Sue, we need to know how fast Sue was. Well, she ran 2 kilometers in 8 minutes. So how do you find speed? Or in science class, sometimes you call this the rate. Well, rate is distance divided by time. This is from your science class. So if she went 2 kilometers in 8 minutes, this would tell me her speed. So if I took out my calculator, and I'm going to open my calculator here. Sorry, I should probably already had it open, but we'll take a second here while it opens up and loads up. If I have 2 kilometers divided by 8 minutes, I divide that, it gives me 0.25. That tells me 0.25 kilometers per minute. Or 1/4 is what that would be if you went math, enter, and change that back to a fraction. That means she's basically going 1/4 of a kilometer, or 0.25 kilometers each minute. That's how fast she's going. So that's how you figure out speed. It's the distance divided by time. Just like in your car, if you drive 30 miles in 1 hour, you're going 30 miles an hour. So, how do we write an inequality for the average speeds of runners who were faster than Sue? If this is how fast she was going, how do we graph something, write something that is faster than her? Well, that means the speed, or if you want to use R for rate, or R for other runners, their speeds would have to be greater than 0.25. Notice I did not put equal to, because if they're faster than her, then their speed is not going to be 0.25. It's going to be greater than 0.25. So how would I graph that? How would I show that on the number line? Well, if 0's here, 1's here, 2's here, 0.25 would basically be about right in here somewhere. And then I would shade to the right for numbers that are faster. Now let's think about this logically for real life. Would this continue forever that way? Probably not. In real life, we couldn't have some runner running, 2 kilometers per minute, 2,000 meters per minute. That ain't going to happen. I'm sorry. That is extremely fast. Now, you could have somebody running that fast for a very short distance. If you're talking about Usain Bolt, he's running 100 meters, he's pretty fast. But you're not going to see somebody running that fast for longer distances. All right. Now let's take a look at solving one-step linear inequalities. If you want to write this down, you can. I'm not going to force you to. It does help you because when you take your test, you can have your notes with you. So if you want to write it down, that's fine. Pause the video here. Solving one-step linear inequalities is like solving a normal linear equation. You isolate the variable using inverse operations. So essentially, that stuff we practiced at the beginning of this video, we're going to keep doing the same thing. There is one small difference, and this is something you have to watch out for. We're not going to get into the deep theory behind this, but one key difference is that when you multiply or divide by a negative number, notice what it said. When you multiply or divide by a negative number, not with a negative number, but by a negative number, you have to reverse the inequality symbol. We're going to look at that in just a little bit, but essentially what happens if you don't do that, if you don't reverse the inequality symbol, you're going to give somebody the wrong solutions that do not actually work for X. So let's take a look at the first one. Again, you're welcome to try it ahead of time if you'd like to, because if you're solving this, essentially you solve it just like a normal equation. I think most of you can get X by itself here. If you don't want to try it, that's okay. Just keep watching. So X plus 5 is greater than or equal to 3. So what we're saying is whatever number is here, added 5 to that number gives you something that's greater than or equal to 3 always. What is that number though? Well, we take and we solve this just like normal. How do we get rid of plus 5? We subtract 5 on both sides. Now, I know this is an inequality, It's not an equation, but you still have to use that technique of what you do to one side, you have to do to the other. So we subtract 5 and we get x is greater than or equal to. Notice I didn't switch the inequality symbol here because I did not multiply, I did not divide by a negative. So I do 3 minus 5. I'm just subtracting. That would be negative 2. Now what does that mean? X is greater than or equal to negative 2. That's the answer. That means all the x's have to be greater than or equal to negative 2 to make this true. But what that means, on the graph, thinking about what we did just a minute ago, if we had negative 2, negative 3, negative 1, 0, had some numbers on the number line. If you graph this guy, you would have a solid dot or bubbled in dot at negative 2, and numbers that are greater than negative 2 would be this way. And that includes all the positive numbers this way too, like 1, 2, 3, 4, 5, 6, 7. What it tells me is that if I pick any of these numbers over here, let's go with negative 1. If I take negative 1 and I plug it in for x, what that would do is that would give me negative 1 plus 5. Wow, sorry, let me take that back off. Negative 1 plus 5. It should be greater than or equal to 3. Well, let's check. Negative 1 plus 5 is 4. Is that greater than or equal to 3? Yes, it is. It's greater than 3. And so what it's saying is that any of these numbers this way will give me an answer that works for this inequality. That's the whole point of solving, guys. Solving gives me things that work. It gives me answers that actually are solutions. All right, so let's try it again. You can try this one on your own first. So pause it and try it. Notice on this one, the variable's on the right side here. That doesn't change what you do. This is n minus 4. So if I want to get n by itself, I'm going to add 4 to this side, add 4 to this side. So that gives me n. And I've got this greater than symbol here. And then negative 2 plus 4 is 2. Be careful, though, because this doesn't say that n is greater than 2. It says 2 is greater than n. Read it left to right, just like you would a book. And what it's telling me is that the values for n are actually smaller than 2. The alligator's eating the 2. Again, I know that sounds goofy and kindergarten-like, but that's how you can look at it. So basically we're saying that if you put an open dot at 2, because it's not equal to, and you shade the numbers that are less than 2, these are the numbers that would work, because these are the numbers that are going to give you numbers less than 2. All right, try this one. And I'm sorry, that one kind of got jacked up a little bit. Let me see if I slide that. Oh yeah, look at there. That kind of looks a little better. We'll go with that. That's a divided by 4 is less than or equal to 12. Well, what's the opposite of dividing by 4? Multiplying by 4. Now I'm going to do this one in a different color here. I'm going to show you that I multiply by 4 on both sides. So I take this and I multiply by 4 on both sides. Notice that I'm multiplied by 4. Okay, so I'm going to go back over here. Remember I told you there is one different rule you got to watch out for. When you multiply or divide by a negative number. Guys, 4 is not negative. I'm not multiplying by a negative. I'm multiplying by positive 4. So when I multiply by 4, it cancels out and leaves me with a. 4 times 12 is 48. And so notice, again, we did this one with an equation earlier, but it's the same process. Now, if you were thinking about the graphs of this guy right here, 48 would be here, and we'd have a solid dot, and all the numbers that are less than 48 would be this way. So this would be 47, 46, 45. Those are all numbers that are less than 48. But it can be equal to, so that's why we have a solid dot on this one. Because when you have something that's not equal to, you put an open dot, solid dot for things that are equal to. All right, try this guy. Now on this one, I probably got a couple of you because this is one where you got to watch out. Notice that this is negative 4.2 times m. So the opposite of multiplication is division. So we divide by negative 4.2. We divide by negative 4.2. So that doesn't change how division works. But what it changes is if you are dividing by a negative on an inequality, you have to reverse the inequality symbol. So what that means is on this one, I divide by negative 4.2. I have to switch this symbol around from a greater than symbol to a less than symbol. But division doesn't change. I still take 6.3 divided by negative 4.2 in my calculator. That's still regular old division. Negative 1.5 is the answer. That's not different. That's normal division. What changes is I have to flip the symbol. Now let me give you just a basic reason for why. When you look at your solutions here, negative 1.5, 0 would be here, and negative 1 would be here, and negative 2 would be here. Negative 1.5 is right here, so you do an open dot at negative 1.5, and then you would shade to numbers that are less than because the alligator's eating the 1.5, so you'd shade this way. So we're talking about negative 2, negative 3, negative 4. Those are answers that should work. And if you take negative 2, I'm going to use negative 2, and you plug negative 2 right here, it should be greater than 6.3. Well, let's check it. If you take negative 4.2 times negative 2, you plug in that, it gives me 8.4, which is bigger than 6.3. If you take one of these guys over here, let's say 0, and you plug in 0 right here, 0 times that would be 0. So you would have 0 is greater than 6.3? No way. 0 is not greater than 6.3. So what that tells me is that these answers over here do not work. That's why they're not shaded. That's why I have to flip the symbol. Because if I didn't flip the symbol, I would be shading this way, and that would be wrong. So guys, really the reason we flip this symbol here is because it actually tells us the correct answers. And I know that's weird. We're not getting into the theory behind it. I'm not going to go into some crazy stuff of trying to teach you the in detail reasons why. But when you divide or multiply by a negative, you got to flip the symbol around. All right, so that's basically everything from this first lesson. So now what we're going to do is we're just going to try a couple. I'm going to get you to try solving a couple on your own. So I want you to pause it, try it, and then watch the solution. So on this one, we're dividing by negative 6, so we multiply by negative 6 on both sides. So we take it and we multiply by negative 6 on the left, we multiply by negative 6 on the right, but remember what I said, if you divide or multiply by a negative, you flip the symbol around. Negative 6 times 3 is negative 18. So the opposite of division is multiplication, but if you multiply by a negative, and guys, that's the key, is what you're multiplying by right here, not what you're multiplying with. It doesn't matter the 3. It matters that you're multiplying by a negative on both sides. That's what you are doing to get rid of the negative 6. Here's another one to try. So if you tried this one, hopefully you realize this is 3 times x. So the opposite of multiplication is division. So we divide by 3. Notice on this one, though, I'm dividing by 3. I'm not dividing by negative 9. So be careful. Do not flip the symbol. Negative 9 divided by 3 is negative 3. Guys, it's not the fact that you have a negative in the problem. It's the fact that if you multiply or divide by a negative. I think I've said that several times now, so hopefully you're getting the point. All right, so what I'm going to do is I'm going to post your homework probably sometime later today or tomorrow morning, because I want to try to make you watch the video first. So I hope you guys are doing well. I hope you're staying healthy. Let me know if you need anything, please.